Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you all for coming. It's my pleasure to welcome back Andreas Zeller. He actually visited us many times, like he spent time here as visiting faculty, I think 2 or 3 times now. And today he's here only for 1 day, but to give you some background, in case you don't know Andreas, he's professor at Saarland University in Germany, and he's also ACM fellow. He organized many conferences. He's very well known and respected in the field. And today he's going to talk to us about his latest research on App Store mining. Okay?
Yeah. Thank you very much, Tom. And well, we don't have the PA on, but I hope you can hear me all right. There's not that many in the room today, but it's going to be maybe a bit more interactive. So feel free to interrupt with questions anytime you like. So this is our first investigation into a field called App Store mining, where we are looking into applications as you find them in common stores. In our case, the Google Play Store, which holds all the Android applications. And we're looking at a very general question here, and that is whether an application does what it claims to do, which of course is, well, this is, in all generality, it's one of the very fundamental questions of computer science. And yes, we definitely had some fun doing that. And let me tell you a bit about what app behavior here means, what app descriptions mean, and what the checking process is. Let me motivate you with a simple app as we found it in the Google Play Store. This is London Restaurants. London Restaurants with the screenshot, and this is the full description as you see it as a regular user when you want to download it. It's free. It's free and offers a lot. It gives you a full list of restaurants and pubs in London together with the type of food, and you can search for specific kinds of food near you and whatnot. So it offers all the usual stuff for classical travel and food applications. The interesting thing about this app is that on top of what it claims to do, which it actually delivers, it also gives you a couple of extras. In particular, this application accesses your account information, so including your mobile phone number and your device ID, and sends all of this out to some unknown server. So, and of course, none of this behavior is made explicit somewhere in the description. You could think that an application that goes and takes your mobile phone number and sends this around for arbitrary usages is malicious in the first place. But that's actually not true, because the question, what makes an application malicious, very much depends on the context. There's applications, say like WhatsApp, for instance, which is very popular, or possibly the most popular instant messaging application on Android and on mobile phones, which happily does this just as well. In order to function, the very, very first time you start this WhatsApp application, it actually takes your entire phone book and sends the entire phone book back to the WhatsApp server in order to check whether any one of your contacts with that phone number is already registered with the WhatsApp service. So the simple fact that an application sends out private information does not make it malicious in the first place. The question simply is, the question is more whether the behavior comes as a surprise to the regular user or whether it does not come as a surprise to the regular user. So we could say, if an application does something which is covered, which happens somewhere in the background, and in particular which is unadvertised, any of these behaviors, this is what we're looking for, and this is what we as regular users would be surprised. So, and this is something which is particularly true for this London Restaurants application, because London restaurants, this is a travel application, travel and mapping. And while a travel and map application would, for instance, happily access your current location, that's pretty normal for mapping applications, accessing your mobile phone number is not part of what a travel application actually has to do. And therefore, accessing such account information and sending it around is abnormal in this particular category, which is different from the messaging category. So what we do in this work is as follows. We have set up a tool chain, which is named Ciabatta, which stands for checking application behavior against descriptions of applications. Ciabatta is also a French word. Anyone in French here? Is also a French word denoting a specific rhythm in jazz. I think there's a song, Chabadabada, Chabadabada. This is a famous French film music from the 60s. Un homme et une femme, a man and a woman, 61, I think. And this is where this specific rhythm comes from. So if you're interested in French jazz, you recognize Ciabatta. Last time I gave this talk, there were two people in France who noticed that and who immediately burst into laughter. So apparently it strikes a chord. So, well, okay, good. we've had enough puns now. Good. So this is what we're doing in Ciabatta here. We are taking a number of apps. We are collecting a large number of applications. We are grouping these. We are identifying the topics that these applications deal with in their description. Then we cluster them according to the topics that are dealt with in their description. And from that, within each cluster, once we have found that we have a number of applications that all belong to travel and mapping and map themes, then we look at the APIs these individual apps are accessing, APIs as proxies for their behavior. And from that, we look for outliers if there is any application in that cluster which has a different API, which accesses different APIs than the other apps in that cluster. Then we want to identify it as an outlier. So this is what I'm going to show you today in this talk, including the outlier detection.
Question about the clustering. Can I think of each topic as an adjective, any number of which can be applied to a particular app?
I'll come to that in a second. I'll identify the individual steps, and then I'll be happy to get back to your question. Let's go a bit and check the individual steps in here. The first thing we did is, well, in order to do that, you need a collection of apps, which is what we did. So we spent a total of 4 months running a script that would download apps from the Google Play Store. We checked all the 30 categories in the Google Play Store and would download the top 150 apps as well as their metadata, which is the description, the rating, user comments, and all that, which is something we did last winter and last spring. We only looked at free applications because, well, for simple reason, my university cannot afford to pay for plenty of expensive apps. So it's just the top free apps. This gave us a collection of 32,000 apps. Actually, you have to run this script for quite some time because if you download more than a few dozen applications a day, Google is going to block you out because they would reasonably assume that you're simply that you're not a regular customer. And we actually made a data package which contains all the metadata of all these apps, and this is available on the website. I'll come back to that, and I'll come back to that at the end of my talk. So this was our collection of applications, and this is what we wanted to analyze, and this is where we wanted to. These are the apps where we wanted to learn which descriptions normally correspond to which behavior. Next thing is, so we get all these natural language descriptions of applications. So what you need to do next is you need to do some natural language pre-processing on this. For instance, you have to get rid of stop words. These are words that commonly occur in English language, such as you, for instance. You don't care for that. And you also have to normalize the individual words. For instance, turn plurals into singulars and likewise, such that you get a vector overlap. So this is what this looks like. So see, you are in. All these stop words all these common stop words would be removed, and this then gives you a vector of words that describes what the application is doing. And these are the words then within each description that characterize the behavior of the application. On this, on these sets of STEM words in the description, we would first eliminate all the applications whose descriptions were, well, close to being empty, which actually eliminated a third of all applications because they were literally close to no description at all in there, which is something I find surprising, but apparently people download these apps even though they have no description. And then we used a standard technique for topic analysis, which is called a latent Dirichlet allocation, LDA, which would take these words and group them into topics that frequently occur together. So you take the word that frequently occur together and you apply LDA to put them into 30 groups. And this is a standard technique. So for all the natural language processing, we didn't invent anything new because we're not exactly natural language processing scientists, so we stick to all the standard techniques as we always do when we are venturing in different areas. These are the individual topics that we came up with. So we had 30 topics overall. We gave them individual words, but these are the most representative words in there. So here's Galaxy, Nexa. Well, you can identify the brand names in here. Device, screen, effect, install, customize. So this is a cluster of topics that all relate to personalization. Game, video package, game, video page, sheet, link, and so on. This is for games and cheat sheets. Slot machine, money, poker, currency, market, casino, coin, finance. This is all related to money, and so on. So we had a total of 30 topics from top to bottom. That all relate to various aspects of topics an individual application would address. Yes?
I have a question about how these apps are categorized in the App Store. So
yes.
What I'm wondering is whether there are categories like this already assigned to these applications.
Yes.
I suspect there are.
Yes. The applications actually already come with categories. That's right. There's a librarian which does that. But there's two things. For one thing, we would find clusters that you would not normally find in a store. For instance, we had an ads topic in there, which is we had applications that, from their description, make clear we have plenty of ads. So that's clear because we have words like a notification, policy, share, air push, advertise, all this is in there. But in a regular store, I very much doubt that you would find a category of ads because normally, well, this would imply that you as a user would specifically search for that category, which normally you don't. No, I'm not too aware of this. So we wanted to have something that we actually needed something that would abstract away from the categories found in the store. The second reason for that is that the categories as we found them in the store did not suit our purpose very well. But I'll come to this later in the evaluation. Yep.
I guess the better known an app is the fewer words in its description.
Could be, yes. If you have something like Angry Birds, we immediately can identify what's about Angry Birds. And Angry Birds is in there too. What's happening with the screen here? Oh, here we go. Touch screen to make monitor.
More generally, maybe text doesn't have enough of the context information to identify what an app is supposed to do.
Yes, that's right. We can in the longer run, you can also imagine that if you have some sort of brand names like Angry Birds, for instance, you could actually say Bing the whole thing and then check for reviews and check for additional information about what would be commonly associated with that.
And if you go to Google Play Store,
Yes.
When you click an app, you see similar apps. I assume that Google does some kind of analysis to cluster apps.
Yes,
that are similar to
Google can do that because what they do is they know which applications are downloaded by individual users, and so they can recommend individual apps to you based on the download history. They will tell you people who downloaded this application also downloaded these other applications. This information we did not have, so all we had was the description. We would not know the individual purchase history of individual customers.
I'm looking at the Google Play. Oh, I don't want to. But I'm looking at the Google Play website right now, and you can see that here it's a similar apps. Those are all kind of similar in terms of functionality.
I very much assume that Google employs a number of librarians who actually take care of provisioning the store and organizing it. Given the results we have, this is not always clear that Google has that, because I'll come to that in a second. But in principle, yes, you would assume that a well-kept app store would have a number of people who actually take care of filling the shelves and organizing them. But what we found in the Google Play Store was that Google apparently does not very care so much about what they're actually offering in there. Okay, for the London restaurant application, so every application could address multiple topics. For the for the London restaurant application, this would end up in navigation and travel. This is the first topic. It's also about food and recipes, and it's about travel. So this is what we get now. For every application, we have a set of topics that this application addresses. Next thing in here is we would go and we would cluster these applications. We would cluster these applications according to the topics they deal with, because applications would deal with multiple topics. And the idea here is we wanted to have groups of applications that are similar according to their descriptions. And for this, we used, again, a standard techniques, the k-means technique, to identify such clusters. And for k-means, you need a number k in order to identify the number of clusters. And there, again, we use the standard techniques, the so-called element silhouette, to identify the best number of clusters. And the clusters, again, we have 32 clusters in here. The clusters are very much in line with the individual topics. So if your most dominant topic, for instance, was puzzle and card games, we would have an appropriate cluster for that. We'd have a cluster of applications, memory puzzles for music videos. Religious wallpapers was a category, was a cluster which I was not aware of, but apparently there's hundreds of applications that do nothing but display your favorite religious symbol somewhere, or customize your screen in order to reflect that. So all of this is in here. We also have adult photo and adult wallpapers for those of you who are interested. I'm happy to report that this was joint work with Alessandro Gorla, Ilaria Tavecchia, and Florian Gross. Alessandro and Ilaria were in charge of looking into all the individual applications and check for misclassifications, and these two girls were the ones who checked out all the individual adult applications. We had plenty of laughter from their room, and we as men wouldn't want to know anything about what they saw. So yes, you get you get the full breadth of human activities reflected in these applications. Okay, so these are now 32 clusters, and now in each of these clusters we would have a set of applications. For instance, in the Personalize cluster, these are the individual words as they occur in the descriptions of the Personalize cluster. So the Personalize cluster is about themes and launchers and lockers and choosing and design and whatnot. Okay? And this is very different from, say, the travel cluster. The travel cluster would be about maps and information and searching and travel, of course. So these, and this is how you can see already from the word clouds that the applications in each of these clusters are very different from each other. So now comes the next part. For the applications in each cluster, we wanted to identify outliers as it comes to behavior. And as a proxy for the behavior, we simply looked at static API usage, which is fortunately not too difficult, because each APK, this is the binary form of Android applications. You could use a simple static analysis to check which external APIs are being used. However, we did not look into all APIs that were being used, say all the string API calls and whatnot. This is not very interesting. We only considered those APIs which are sensitive, which means that they would be governed by a specific Android permission, meaning that the application, if the application wants to use one of these sensitive APIs, it specifically has to declare so in its manifest. So if an application wants to access the location, it has to ask for a specific permission. And this would also, in principle, be presented to the user when the user wants to install the whole thing. So the user has to explicitly grant the permission to have the app use his or her current location. So for London restaurants, the APIs being used look like these. So these are all the sensitive APIs that are being used. So from the sensitive APIs, you can already see, well, it accesses web pages. It accesses, well, it accesses servers via URL. It uses the notification manager. It checks whether Wi-Fi is on, whether the network is connected. So all of these are sensitive APIs. And these sensitive APIs are governed by a set of permissions. These are the appropriate permissions. And you can see in here, so it needs to access the Wi-Fi state, network state. It needs to access the current phone state. And among others, it also needs to get access to your account. Well, that's what it claims. That's what it claims it needs. And if you now look at all the APIs that are being used in the travel cluster, or specifically all the permissions that are being used in here, you see that these are also these are also very characteristic for the individual apps. So all the applications in a travel cluster typically need to access your current location, your precise current location, which is obvious, and they also need access to the internet. This is what makes a travel application. Whereas a personalized cluster has means to access the external storage. It works over the network. It is able to turn on and off individual components. This is what makes it personalization. And so you can see that not only do these clusters very much differ by their descriptions, but they also very much differ by the APIs by the APIs and the permissions that they commonly need. So this is what we have now. For each application in our cluster, we can check the individual APIs that are being used in there. And now comes the next part. We check for outliers within each of these clusters. So again, here's a travel cluster with all the permissions of APIs used. And this is generalized over all applications in that cluster. And now let's take a look into London restaurants. This is one of the applications in that cluster, and you can see that there definitely is a difference in here, because London restaurants uses APIs which are related to the get accounts permission, which are APIs which are not used by any other application in the travel cluster. Which means that this is an outlier, and these three API calls which are in bold in here are precisely those API calls which are unusual for that cluster. So the question is, how can we identify such outliers automatically? For this purpose, we used a so-called one-class support vector machine, which is a variant of the well-known support vector machines, which are commonly used for classifying. But in this case, we use it for a different purpose, namely for identifying outliers. For each APK, we put in a vector of, for each APK in the cluster, we put in a vector of the sensitive APIs and the number of call sites for that API. And what the OCSVM does is, like any SVM, it creates a plane, well, an n-dimensional plane that tries to get as near to the individual applications as possible. And then you can identify the distance between that plane and the individual applications. And from that distance, you can then identify, well, here's an application which is far away from the norm, which is an outlier, which is different in its features, and therefore this is a likely outlier in here. So, and this is also precisely what OCSVM would identify in here. London restaurants would be properly identified as an outlier because by its usage of APIs, it would simply differ from the norm. So, and this is what Shibata gets you in the end. All these steps are fully automatic, I should say. In the end, what it gives you is a ranked list of outliers with respect to the API usage within each of these clusters. So, the question is, does this make any sense? So, what are the outliers that you what do the outliers look like that you actually get there? This was fun work because you get to see a lot of apps this way. So what we did was a simple thing. In each of our 32 clusters, we identified the top 5 outliers, and then we looked at them. We identified them, which we checked what they would actually do and how this would correspond to the description. And I can tell right away that 26% of all these outliers showed behavior that A, used sensitive APIs, B, was not advertised, and C, acts against the interest of its users, such as, for instance, accessing sensitive information, propagating this without being advertised in any place.
How did you know that it was doing this? Did you use the app or?
We used the app.
Okay.
We started the app, we ran the app, we used the standard debugging techniques in order to identify which information was accessed, where it went. So this was a bit of standard. Well, so good thing was that these applications were not malware per se, so they didn't use any sophisticated obfuscation techniques to disguise their behavior. So far, so good. So by using standard techniques, a debugger, and checking which APIs are being used, we could very quickly find out what they're actually doing.
So I might be getting ahead of you, but I'm curious what the other 75%.
Yeah, I'll be getting to that in a second.
So related to Chris's question, so a lot of these apps are interactive apps. So I was wondering how you got these traces automatically.
We wouldn't. So for the evaluation, this was manual work. So we actually interacted with them, and we checked whether what we get in the outlier description, whether this actually made any sense.
But you have thousands of applications that you are trying to classify based on their runtime traces, right?
Nope. So far, what we did is all automatic, A, and B, it runs on. We are checking API usage statically. So all of this does not require execution.
Okay.
But in fact, we assume that in the long run, a simple static analysis of APIs will not suffice. So we're looking into more fine-grained stuff, and I'll come to that in a second. And you also had a question, or let's just proceed a moment. Yep.
I have a hesitation. So you don't have the source code, but
We don't have the source code, no.
So statically, how do you catch that it's using the APIs?
We simply know that it declares that it has a dynamic link to the API, so that's what it is. Number two, it uses it requires the appropriate permission to use that very API. So the API usage is not there by accident because otherwise they wouldn't have to declare the sensitive information too. So these are this, but of course we don't know whether the API is actually ever being called.
Oh, this is
That's
all declarations in the meta.
it's yeah. You can think you can think of a think of a binary which is dynamically linked, and you have an external reference to some API, and this is precisely what we're identifying there.
So I'm now confused on what the input to the support vector machine was, because you said number of calls to the API
Yes.
was the... Okay, so what is that number? If you don't have access to the source to see how many calls to the API were made, how many...
We know the number. We know the number of call sites because you can do a simple binary analysis to identify the number of jumps into that. You look at the bytecode, yes, straightforward. Nothing more complicated than that. And if you ask me whether the number of call sites is needed or not, I would love to tell you that, but I don't know. We simply started with the number of call sites, and that's what we had in the beginning.
The store doesn't enforce anything like any API call you use, you have to tell us about that and use
No, but if you want to access a sensitive API, you have to declare this in the manifest by requesting the appropriate permission.
Some people just click OK, I guess.
Users generally, as far as I see, click OK to even the most click OK even when installing the most outrageous, even when asking the most outrageous behaviors. So we have experience with malware. There's an Angry Birds game. You started. It asks, we want you the ability to send SMS. And you wonder, why do you need to send SMS? Because that's how we finance ourselves. See, if you like the game, after a couple of games, you can send an SMS and to some premium number. This is why we need that, only for that, of course. What the application in reality does, it starts out churning out premium SMS the very moment you start it. So, yeah, well, it's not always easy. Okay, let's come to some of our, let's come to our stuff, what we found in there. First and foremost, outliers. We found plenty of applications that use ad frameworks. There's AppLovin and AirPush. This is, many of these free apps finance themselves through ads. So far, so good. What's interesting, though, is these ad frameworks give you, as a developer, a higher percentage of revenue if you allow your app to access more sensitive information. Meaning that the more sensitive information your app accesses, the more money you get from your ads. No, that's simply because they gain more information about you, which is more marketable. So if they not only know, so if you just send an ad to some anonymous user, yeah, you get a small share. But if they know where you are, if they know who you are, if they know what's your mobile phone number, such that they can text you messages or whatnot, yes, you get a higher amount of money. That's the sad reality of ads in games. That's what we found in here. We also had strange behavior in there. We had what do we have? The game, for instance. What was that? The game requires access to your microphone, and explicitly asks so. So there's no feature in the game which actually does that. But maybe this is targeted to some head of state. We don't know. You install on your.
There is a part of that game, at least the physical one, where you actually are supposed to yell out Uno.
Yeah, that's right. That's perfectly fine.
Right, no, but that's why you buy
It is Angela's favorite game now, right?
I have it in my notes in here. 1 second. Here we go. Wonderful. Yeah. What else do we have?
She's one of the spy down.
Yeah, Wicked is the official application for the. No, sorry, I was confused. Wicked is the application for the musical. This is the one that accesses your microphone. Needs your location. Possibly in order to figure out whether you're sitting in front or on which side of the chair you're sitting. I'm not sure about that. Yahoo Mail. This is Yahoo Mail. Is also able to send text messages. It asks for text messages and apparently it can send them. But of course, this is not advertised anywhere.
Some of the mail people use text messages as verifiers. So they
yeah.
say here's the
yes, that's right. That's right. But then you would have at some point during your user interaction or in the description, you would have some notice that tells you that this is actually the case. Nothing of that found in these apps.
Did it actually send SMSs when you were using it? You said you ran these applications.
Nope.
No,
it didn't. We didn't see it sending, but it explicitly requested the permission to send out SMS messages. I have no idea why. I have no idea why this is in there. Okay. We also had applications that didn't fall into the right clusters. SoundCloud is an example. This is an application where you can actually record audio and send this around. And this ended up in a sharing in a sharing cluster. However, recording audio is uncommon for sharing applications. This actually means that SoundCloud actually is a mix of somewhere between audio and sharing, and well, it had to fit into one of our clusters, so that's obviously room for improvement. We also had an application called Hamster Life, which ended up in religious wallpapers and promptly triggered, probably became an outlier in there. We have no idea why this is the case. And here's my favorite example. This is Mr. Will's Stud Poker. This ended up in the game and money cluster, and it was the only application in that whole cluster that would not display ads. And since it would not display ads, it was immediately identified as an outlier. So what you see in there, outliers, does not mean it's good or bad. It simply means it's uncommon. It shows uncommon behavior. And well, if it does not show ads, then this is uncommon behavior.
So, okay, remind me what the features are to the SVM. Is it just the APIs?
It's just the APIs, the set of APIs, yes. And this stud poker game does not access the internet, and what you normally need for access application.
But it's the fact that you
Exactly. Yeah, that's the thing. So yes, so you can also have outliers in these clusters, which are simply uncommon behavior, but in this case, actually, it's one good behavior in a whole set of bad behaviors in there. Speaking of bad behaviors, we also did a second round of evaluation, and that's even more fun. We also took a set of known malicious Android applications and checked whether these applications, how these applications would end up, whether they would end up as outliers or not. So for this, what we did is we trained the OCSVM now as a classifier on 90% of our benign apps, which we downloaded from the store, which was fine. And then we had 173 known malware apps in which we used the OCSVM as a classifier, and then we wanted to see how these benign apps as well as our known malware apps would be classified. And this is what we got out here. So these are all these of course are average numbers over multiple runs and multiple splits. So from our malicious apps, the vast majority was also predicted as malicious. Smaller part was predicted as benign, and our benign apps, a large majority was also properly predicted as benign. In percentages, 84% of our benign apps were correctly predicted as such, and 56% of our malicious apps were also properly predicted as such. And this is, and of course, if you do have a malware scanner on your Android app, you will get much better results. But then such a malware scanner actually checks against patterns of malware that are already known. Okay, so it has a history that it can check against. Whereas we can take an arbitrary app, which nobody has ever seen before, and the description and its APIs, and find out that what it claims to do does not correspond to what it actually does in terms of API usage. So this, as a sole detector of malware, this would not be enough. But if you combine this, with patterns of known malware, if you bring this together, this can be an excellent combination. Checking against new apps which nobody knows anything about, just checking what they claim to do and what they actually do. Here again, this is the correct classification with clusters. We also check the individual components of our Ciabatta approach. So this is without clusters. You see that without clusters, the detection rate of malicious apps immediately goes down. So all of this clustering, according to descriptions, actually is needed. And also, you asked beforehand, the Google Play Store also has categories. That's right, which is what we did too. And we checked for the categories given from the Google Play Store, and you can see that our clusters also are better than what we find in the Google Play Store. Also, we require less because, well, we don't actually need any such categorization in the first place. So this is what we get in our second second evaluation. So we can improve or even enable malware detection, which is good. We're better than the given categories, and we don't require any prior knowledge about what makes malware or not.
I just have a quick question about this evaluation.
Yes.
Where did you get the 175 malware apps?
This comes from a standard paper. I think the name is Android Malware Dissected, where researchers, I think this was 1 or 2 years ago, where they brought together a collection of malware, which they made available for download, which was the precise set which we used in there. However, we only looked at those malware, we only looked at those applications for which we could actually find a description, including copies of Angry Birds, where we actually looked up the official description from the Play Store for Angry Birds to associate this with a name. So this was relating to the question you had earlier. So you find something that's called Angry Birds APK, okay? And so we associated this with the description of Angry Birds from the Google Play Store and used this as a classificator for the malware, okay? And then what you would find then is, so if this APK would be nothing like Angry Birds, nothing at all, would not even look like a game at all, it would immediately be flagged as an outlier. But even if it would fall into the correct cluster based on its description, and then again we would identify, well, it does a couple of things differently from the other games, and again would be flagged as an outlier. And that's, I'm not saying that this is going to be the ultimate tool in malware detection. It won't be. But if you have something that's totally new and have nothing else but the description and its behavior, this can help. This can help you a lot identifying, well, the worst offenders in the first place. Okay, a bit of current work, and we're running out of time. As I said, we're not experts in natural language processing. We can do much better than that. One can make use of ontologies. One can make use of, what's the plural of thesaurus? It's thesauri. Of synonym dictionaries. Okay, that's maybe a bit easier. That's things we can do. We can also go and create explicit mappings between topics and behavior, figuring out here's a topic and these are the APIs that are the combinations of APIs that would be associated with that topic. We can look for much better features of individual applications. Information flow is our number one candidate. We're heavily investing into that. And also checking whether any of this behavior is actually authorized by the user. Something like a dialog pops up asking, we'd like, in order to continue play, please allow us to send this text messages to this premium number, which is going to charge you by so much. Are you okay with that? Yes, no. At this point, when you say yes and all the information is there, it's perfectly legitimate at some point, but this is also something we don't see at this point, okay? This is part of looking into the information flow. Problem with these problems with these letter points is, as you already pointed out, if you want to do all of this by static analysis, you'll run into problems because including some of the apps we found, and definitely malware does that, you have plenty of features that make static analysis very hard. I mean, as soon as you set up an interpreter of your own, of a language of your own, or even a subset of a language of your own, your static analysis essentially stops working. We also have instances of code that gets sideloaded, that gets created on the fly, or that is just normally obfuscated. So all of this will make your life hard if you do static and symbolic analysis. And in practice, this means that,
One additional thing the slide is, what
Hmm?
about a sound recorder application that
Sorry?
also, what about a sound recorder application that also spies on you? So it has
Yes.
a genuine purpose for using an API, but it also has a
Yes.
the same API.
Well, the thing is, that if the sound recorder does what it says I'm recording sound and don't install this, only install this on your own device, and never install this on someone else's devices. Well, we can only tell whether it does what it claims to do and what, and that's it. But
This is not going to detect subtlety of it, so
Mhm.
There's a limit.
Yeah.
mhm. we can only tell you beforehand, this is what it claims to do, and it does this well, or it won't. But what you make, the use you make of it is not something we can check afterwards. Yep.
what do you mean by remote code?
A remote code. Remote code simply means there's some sort of behavior which happens on the server which you don't know. You see, you invoke some service on some server, the result comes back and you have no idea what's happening, what's happened there. Mike?
So much of your analysis is based not necessarily on what's in the bytecode, but what's in the manifest.
Yes.
Because the manifest tells you what capabilities
Mhm.
the application
Requests. Yeah, yes.
And if it doesn't ask for that capability, then it's not able to call those certain APIs.
That's right, yes.
Are they able to call those APIs using any of these tricks, or does Google somehow prevent this because they do dynamic monitoring to make sure that
Google does some dynamic monitoring, yes. But Google does some dynamic monitoring. They have an application in place which is called Bouncer, which actually clicks randomly around on the application in order to see what it's dynamically doing. But if you wanted to set up any covered behavior in your app, the simplest thing to do is to check the network you're in. And if your network is Google's network, you behave just perfectly. And as soon as you leave the Google network, that's when you would start your bad behavior.
So the app could actually use those APIs without asking for those. So an app could use those sensitive APIs
Yes.
without having asked for those permissions.
No. That's not true. They have to ask for that. But what you would normally find is they would come up with some legitimate use for using these apps. If you wanted an application to spy on you, for instance, okay, say using a sound recorder, you would claim that your application has this cool feature of voice command, okay? Say, and now new in this release, control your character by voice commands. And of course, then you need to enable the microphone. And the thing is, once you have, this only happens once during installation. So there's no dynamic check afterwards. With iOS, this is different. So the very first time you access an API, that's when you're being asked whether you want to use the microphone. And then this would be a bit different because you would be asked, the application would ask you in context, okay? So you would say in your settings, you would say enable voice commands, and then you would get a dialog from the operating system asking you whether you want the application to, whether you want to enable the application to access your microphone, which means only at this point would you actually be able to do that. In Google, this is different because you give all these permissions at the moment you install this, and you may even forget about them afterwards. So not all is well in not all is well in these categories. And the fun part is, well, all these mobile devices have all these wonderful sensors and all this sensitive information, and well, they will soon be able to access your heart rate and your pulse and your blood pressure and whatnot. Your fingerprint, yes, that's true, all that. So, yes, so there's risk involved with that.
So I have a question. Sometimes an application in a particular domain may use some sensor or some API, whatever, and that's actually something that is able to differentiate that app, and it's something they want. So like Uno, maybe Eastern location because it's like, oh, find people really close to you that want to play Uno or something like that.
Yes.
When you looked at your top 5 outliers, did you check back with the actual app descriptions, not the LDA summarization, but the actual app descriptions?
We checked with we checked with the so Uno was one of the outliers where we found, well, it can access your location, but we would not be able to tell whether this was against your interest or not. So these 26% was only stuff where we found that this was explicitly against your interest. There's another second category, I think, which is another 14% or so, where we found, well, it accesses your data, but we're not able to tell whether this is a feature or whether this is a feature or something that is directed against you. Okay, so this is the third category was simply false positives, which is, well, something that's unavoidable with this sort of analysis. I'll just like to come to a close. So figuring out the relationship between what's happening on the screen and what's happening in the code is becoming increasingly difficult with static analysis alone. So what we're doing here is we are investing heavily in test case generation, which allows us to interact with the application on this level, and then check what happens on the code level, and then use this whole thing to guide the test generation. And in the interest of time, we can go just here. What we're using here is techniques called search-based testing, which is evolutionary algorithms which start with a population of random inputs, which evolve these inputs, mutating them towards specific fitness goals. And even if you have a very simple way to measure the fitness, these algorithms will be effective, which means that you don't have to deploy your full-fledged symbolic analysis on Dalvik code, but all it takes, for instance, could be a simple measurement which code is being executed and which not. And we are looking into various fitness goals in here, branch coverage, API coverage, meaning that we can guide test generation towards specific APIs, for instance, sensitive APIs. We can guide test generation towards specific information flows, which is very interesting. And all of these fitness functions are very easy to set up. I mean, it takes how long does it take? It takes about 2 to 3 weeks to set up an individual fitness function, and then you will have your generic test generator adapted to the specific runtime feature that you want to look at. And this is a demo we had this year at the Cebit Fair. This is our robot which happily clicks along on an Android tablet. So we are well able on this date to identify individual interaction elements, to click on them, and to guide the entire process. At this point, when we showed the whole thing, we only had a handful of applications on which this would work reliably. But by the end of this year, we're going to expand this to the full roster of applications we're having right now in our set, and then we will be able to look at all these dynamic features too. By the way, at the booth, plenty of people came along and asked, "Hey, you have a robot, that's cool, but why don't you do it? But can't you do this in software as well?" And we said, yes, we can do this in software. It's 10 to 100 times faster. We can do 100 times in parallel, and we can put it all into a black box, which I will put up here, and it will be happily humming around. But it turns out that the black box that humming around doesn't make a good demo, so we had so this robot was a nice attractor.
Grad students,
yeah, sure. I should just set up a cooperation with some Chinese university where they have plenty of cheap work labor. That's what we. Okay, and this is what we actually. This is the overall theme. What we're looking into. So for hundreds of thousands of applications, possibly the totality of all applications there are, we want to be able to gather their descriptions, their metadata, but also gather static features, gather dynamic features, as many as we can, and then find out what's common in there, what's uncommon in there, and in particular learn the common behavior such that we can more easily identify what would be a surprise for future users. And given that we now have these wonderfully populated stores, hint, Microsoft also has some, I think, and given that so far when we in research mined individual projects, we looked at the version history, which is fine, which is very detailed, but we only had access to overall two handfuls of projects. This is fine because we get all the detailed development information, but with this you get an entire new access where you can look at hundreds of thousands of applications and see what's common in these applications. Not so much the development history, but how they behave, and what users can reasonably expect from them. And with that, I'd like to close. So I've shown you our ciabatta approach, which identifies outliers based on descriptions and APIs, which identifies such outliers reliably, plenty of key findings, and a full data set to a 200 megabyte Excel file to be downloaded with all the metadata in there. Well, that's it. Thank you for attention. I'm happy to take more questions.
Even an application that mostly makes benign use of your personal data could occasionally misuse it, right? And there's, I mean, your approach would not be able to catch it, of course. And
yes.
Do you think there's a need for application developers to actually prove that they're making only benign use of one's personal data before they can publish their apps?
Well, the thing is that it won't be easy to tell what is benign and what is not benign. This is going to vary tremendously from between users, also between social contexts. I remember when Apple came up with the App Store in Germany, there was lots of outrage because Apple would censor any application that would show a nipple, for instance, which in Europe is not that much of an issue. Of course, it is in the US. And and the question is, if an application does that, would it be considered malicious? Would it be considered benign? This very much depends on your cultural context.
Sending your email to an advertiser, for instance.
Yes.
Where the app should declare that to the store.
Yes. So normally I would assume that there would be that. So what I'd like to have is that for every sensitive information an application accesses, there should be some there should be some explicit declaration and explanation of what it does and why it does that. And you can think of this as a simple form of consumer protection. Okay, so that's something I'd like to see in our app stores. I don't care. I actually don't care that much whether an application is benign or not, because this is very hard to tell. I just want to make it sure. Just want to make sure that if an application, well, in particular for free applications, okay, which is where it's obvious that they have to that they have to come up with some revenue model in order to finance the development, but it has to be evident to users what these applications do and the risks that come with it. And this is something we don't see in the Google Store at all. There's essentially no regulation at all. So and I'm also not sure what consumer protection agencies think of what's being offered there. Right now, it's Wild West. That's how I see it. And from what I see is that many of the outliers that we have identified have been taken down by Google since in the meantime, not because of our work, but actually because users complain. That's a fine policy, but I would very much prefer if such actions took place before users start to complain about the damage that's being done. So that's what I'm aiming for. Not so much coming up with better definitions of benign and malicious, but protecting users against against surprises they can find in these stores. And if you protect them against surprises, well, as a side effect, you also get rid of many of the malware problems, which is a good thing.
I'm having a hard, I mean, there's a lot here, but I'm having a hard time sort of understanding what it is actually what is actionable in what you've built, because there is a lot here, right? So, and I mean, there is a lot of literature on malware detection, especially for Android. But in some sense, it's like analyzing PHP applications. Anytime you look at one, you find something.
Yes.
So the bar is at this point fairly high, and
yes.
It's not really exactly malware detected.
No.
I think the hard problem that is fundamentally unsolved, actually there was a paper presented last week that tries to address it, is understand the content, which is to say if there is a disclosure, for instance, of some sort, is that intentional or is it not? And ultimately, as you pointed out, there are corner cases where it's not so obvious. Now, how to present the purpose of a particular disclosure to a user? I mean, usable security has no answer to that question. Every possible paper I've read about it has only negative results.
Yes.
So, I mean, and frankly, Android's attempt to have these really fine-grained permissions has made it so that it's impossible for the user to understand anything.
Nope. Yep.
I mean, there's a lot here, and certainly, outlier detection is, profitable in a number of ways, I suppose.
Yes.
But it's not like, given the false positive rates in a sense, it's not a tool in a sense, right? You're not really presenting it as such. So what is actionable, I guess?
So, for me, there's two things in it. First, the approach is actionable in the sense that if you do have an application which you know nothing about, you can check it, you can find out that it does things that are unusual in the first place, which is not enough to which may not be enough to kick it out of some app store instantly, but certainly it is something which should prioritize your scrutiny efforts on this one. Okay, if you say that here we have yet another wallpaper app and it does nothing unusual. Okay, just get it through. Okay, so you can use it for triaging. The second thing is, and when you're talking about usable security, I think that if you indeed go and present users these long sets of permissions and what they imply, or worse description of information flow within applications. Here's the source, here's the sink, here's another source, here's another sink, and here's 134 possible mappings. Which one of these are okay and which ones are not? Totally out of the question. I mean, even we as experts will have a hard time understanding that. But what I think, and we're not there yet, but what I think is, if you can leverage the common knowledge about applications and the expectations that are encoded in there, then you can say, here's Angry Birds 2, it's the same as Angry Birds and it's the same as any action game you've ever seen as it comes to security, so this is safe. That would be a thing. So if you can, rather than coming up with the entire set of things, if you can simply point out the differences between how this particular app is different from everything you've seen so far, or what it enables, the things that make this unusual, and if you have a way to catch this, if you have a way to grasp it, it will. I think there's a chance in there to make usable security much more incremental than it is today.
For triage purposes, I would agree with you. As a filter, as a loose filter of some sort, I think it's always useful to have. But as far as exposing it to the end users think that more permissions is better. Because the application can do more.
Can do more with more permissions, yes,
so
of
say
course.
That there's Angry Birds 2 that also accesses GPS. And, can send emails on their behalf. That's even more wonderful than the previous one.
So what happens in these apps when they deny permissions? I mean,
they won't get installed. Then they're not installed.
They're not installed.
It's all or nothing. It's an all or nothing game.
It's at installation time.
Yeah, it's an installation only at installation time. Yeah, you're obviously an iPhone user. Different, very different for iPhones. Yes.
Yeah, and then we have recommendations on the whole permissions model, right? When I'm asked for something, I know what I'm doing.
That's right.
I mean, it's still easy to be covert about things, I suppose.
This is our very first attempt actually to extract such common behavior from applications. I don't think it will be a solution to the malware problem or to privacy issues anytime soon. But it's good. But I think we're on a good direction here still.
Again, it's a chicken and egg problem in that. I mean, malware is a term that's slightly misused in this context. We call them privacy-violating applications. And what privacy-violating is unclear because intent is fundamentally unclear, right? And so this is kind of a bit of a circular definition. But yeah.
Also, this one is that if people knew this was in the system, then you could game it by actually generating a load of apps with the same phrases.
You could.
So that you're not an outlier anymore.
Yeah,
that's right.
Yeah, but then this is well known. If you advertise your house for sales, for instance, and you say, This is in a district of the town which is known for its vibrant nightlife, whatever, okay? You could find euphemisms for whatever is going on.
Basically, if the outlier is getting somebody's address
Yes.
by these phrases,
Mhm.
then what I can do is generate 1,000 apps.
Oh, yes,
exactly
yes.
those phrases
Yes, of
with
course.
that call. So even though they're not actually downloaded,
Mhm.
it now makes it no longer an outlier.
That's right. Well, once you have such a system in place, you may be able to gain.
Yeah.
But then this is true. But then what you would do next is you wouldn't do this for the totality of all apps that are offered, but you would do this only for apps that are actually being used, and then coming up with 1,000 apps that are there only for generating new common behavior wouldn't help you. So, but of course, this is always, in malware. This is always an arms race, and at some point you come up with something new, you come up with something different. There you go.
Sweet. Thanks.
Thanks.